One thing that's different is we're not told what the mass is or what the weight is that's hanging from it. Instead, what we're told is the maximum tension the ropes can be in. So we're still going to assume or go on the premise this is in equilibrium. So the first steps are going to be the same, but we're going to have to add, kind of think about it a little bit differently to actually solve for what we're looking for. So let's start with what's given and what we're to find to kind of guide us. All right, so what information is given to us? Right, so again, we're given a nice picture. And what else are we told? Right, so a little bit different information this time. Each cable can only withstand 1,000 newtons. So I'm going to label that as T maximum, or T max is 1,000 newtons. And we're going to use that information. So any one cable, 1,000 newtons is its maximum. So what do we want to find? Right, so kind of to expand that a little bit, we want the largest mass the cylinder can have such that no cable exceeds 1,000 newtons. And that's an important thing to think about here. So I'm going to call that M max. So maximum mass that it can have such that no cable exceeds 1,000 newtons of force. So this will come into play in our solution and equation step. The free body diagram is, since we're saying it's in static equilibrium, the free body diagram doesn't really care about this. We're going to care about once we get to the equations. So what's our point of interest in our free body diagram going to be? Right, so again, pretty obvious in particle equilibrium. A, it's attached to all these ropes and then this hanging mass. So A is going to be our point of interest. And we're going to use their coordinate system that's provided. All right, so A is at the origin. And the points that we're going to be interested in are B, C, and D, since there are ropes going from A to each of those points. And D is over here. So as before, it's in 3D, so coordinates are going to make our lives easier. And since A is at the origin, that also makes this problem a little bit easier. So C is at -1, -2, 2. And D is at 3, -4, 0. And A is at the origin. All right, so like we've seen before, what are the forces acting on A? Right, so we can start there. So the mass does not act on A directly. What's acting on A? Right, which is what of the cylinder? Right, the weight of the cylinder. So again, don't confuse the mass with the weight. Eventually we need to get to the mass, but weight is the force. So there is a weight force pulling down. So how much is it? We don't know, and that's okay. So if we don't know something, I'm going to call it W. It's the weight of the cylinder. It will be related to the mass, and we'll get to there then. So the weight of the cylinder, whatever that is, acts on A. And then what are the other things that act on A, as we've seen in the last couple examples? Right, the 3 cables it's attached to, there have to be in tension. So arrows coming out representing those tensions. So TAB, I'll call it, TAC, and TAD. So in the free body diagram, there are now 4 unknowns, the 3 tensions and the weight. So it does labeling look different than what we saw before. And that'll be reflected when we get to the equation step. But the free body diagram is complete here. Everything's at least labeled, and we have all of the coordinates that we need. Now, any questions on the free body diagram part of this? No different really than we saw before. The difference is going to come soon. All right, so the equation step, we're in 3D, we have vectors going off in crazy directions here. So just like before, we need to use unit vectors, or I highly recommend using unit vectors. So in no particular order, we're going to need a unit vector for each of these. W is more obvious because it's in the negative z direction, but the rest of them we need to know. So in no particular order, AD, we're going to get 3/5 I minus 4/5 j. If you had trouble with the unit vector step on the quiz or on the homework, I recommend you go through the steps and make sure you're getting the same values for these when you're reviewing this problem. For AC, we get negative 1/3 I minus 2/3 j plus 2/3 k. And for the AB direction, we unfortunately get decimals for this one. Negative 0.286 I plus 0.429 j plus 0.857 k. Yes, 0.286 I. And we can also put that U hat W, again, negative K hat, just so we make sure we include it in our equilibrium equations. All right, so unit vectors, this makes the next step easier, just like we saw before. Sum of forces x are 0, so what are the sum of forces in the x direction going to be? Right? So again, just pulling out these components, making sure we remember, multiply them by these magnitudes. In the y direction, yeah.
Negative 4/5 TAB minus 2/3 TAC plus 0.429 TAB.
Right? So we see in these equations, the first one has 3 unknowns. The second one also has 3 unknowns. So already, solving-wise, this is going to be tougher to do than we saw in the previous couple examples. So sum of forces in the z direction, what do we have there?
Positive 2/3 AC, TAC. Positive 0.857 TAB. And then negative, well, we don't know. I guess it'd be a negative.
We don't know, but we did call it something. Right, so negative W. Yeah, we'll be able to solve for the W, but we do know its direction. We don't know its value, its magnitude. All right, so these are our 3 equilibrium equations that we have here. So this has 3 unknowns, this has 3 unknowns, this also has 3 unknowns. And our equation 4 here, I'm going to put it here because right now M max does not appear yet. Just so we have something, the mass is just going to be the weight of the cylinder over gravity. So that way at least the equation does exist that we're going to need. Now here's what we haven't, so we've used all 3 of our equilibrium equations, just this mass is weight, or weight is mass times gravity. This one's a little bit different than what we saw before, because again, this is more of a design problem that is an analysis problem. So actually, I'll keep it in the equation step here. There's some additional information or additional relationships. I guess they're not really equations, but they're relationships we have to put in here. So what we were told in the problem is that it's an equilibrium, but we can't have the tension in any rope exceed 1,000 newtons. So as extra information here, again, they're not really equations, but we need to keep this in mind, is that we have these constraints, I guess is a better way to put them. that the tension in none of the three ropes can be more than 1,000 newtons. So we're going to need to use this in a minute here. So what we can do is we can use this information. We have these three equations. I'll ignore equation 4 right now. Between these three equations, we do have 4 unknowns, but what we can do is we want to find, since W is ultimately what we need to find, and then we can find the mass, I want to find each of the tensions in terms of the applied weight. If I know what each of the tensions is, I'll be able to find what weight is going to make that particular rope be at its maximum value. I'll just reinterpret what I have up here. So remember, X was TAB. So TAB, this is still from equations 1 through 3. I'm going to come back to these. But TAB is in decimal form 1.13 W. TAC, put that in decimal, is 0.0484 W. And TAD, from equations 1 to 3, is 0.565 W. So I just rearranged these three things and wrote them this way. All right, so that was the math step. Now I want to put it all together. I have the tensions in terms of the applied weight. Now I can use this information. I am told no tension in any one rope can go over 1,000 newtons. So now I can say this has to be less than 1,000 because that is TAB. This is TAC, so this must be less than 1,000, and this must be less than 1,000. So for clarity, what I'm trying to do, I'm going to get rid of this stuff. These three things must be simultaneously true. So rearranging the first inequality, this tells me that the weight has to be less than 885 newtons. So again, how we can interpret this is, at 885 newtons, the tension in AB would be 1,000 newtons. This tells me that the weight has to be less than 20.7 kilonewtons. At that weight, tension in AC is 1,000 newtons. And the third inequality tells me that the weight will have to be less than 1.77 kilonewtons. Because at that point, TAD is 1,000 newtons. So a common misconception in these types of problems is that we are told that the maximum tension in any of the ropes can be 1,000. And what people want to do is they just set each of these tensions equal to 1,000, and then they solve from there. First of all, you can't do that because now you have too few unknowns in your system, so it's an overdetermined system. And second of all, that's not what's happening. One of the ropes is going to break first before the other two do, and that's what we're trying to see, is to prevent any of them from breaking. So how can we kind of summarize these results here? What's the rule on W? Yeah.
You pick the smallest one.
Right, so if W is less than the smallest one, 885, it's automatically less than the other two. So we can summarize these three inequalities that our rule is that the weight has to be less than 885, because what this says is the first cable, as we put more and more weight on, the first cable is the one that's going to break once we get to 885. Once we go above 885, that first cable is already gone, and then our static equilibrium problem is no longer true because it's relying on there being three cables. At that point, one is broken, and the whole problem changes. So right, 885 is the most weight the cylinder can be. Now we can use that equation 4. So M max, the maximum mass of it, 885 over gravity. So the most mass that cylinder can have is, I believe, 90.5 kilograms. Sorry, 90.2 kilograms. Again, what we're interpreting is once it's 90.2, that first cable is at its maximum tension of 1,000. These are both going to be below 1,000, so they're not on the verge of breaking, but it's when the first one is about to break that our concern comes in.